The Marcus theory tells us that in a soft polarizable molecular material, charge must be intrinsically localized. Even if the material has a large number of sites of equal energy available for the electron to hop to, the price of a reorganization energy must be paid every time the electron changes site. The description of this type of transport, or one description, is Mott variable range hopping. The idea is that we can assume in a molecular solid that the reorganization energies, which in turn depend on local fluctuations, are randomly distributed. So that if we plot a distribution of the number of states available with a given reorganization lambda, they might follow some Gaussian distribution like this. If we take some lower limit on these number of states such that there is a unit probability of finding one to hop to, this would then be the smallest barrier to tunneling, and this would dominate the charge transport process. If we now sample a larger volume of space, so I'll just multiply this distribution by some number greater than 1, you can see that for unit probability, we could always find a smaller lambda minimum, and therefore we would increase the probability of hopping. So if we sit at some site A and explore out a distance r, the number of states within that cube vary like the volume, 4/3 pi r cubed. So as r increases, the barrier to hopping should decrease. However, on the other hand, the tunneling rate will fall with r as e to the minus kappa r, where kappa was the decay constant calculated in Chapter 2. The problem then becomes one of finding an optimal range for hopping. If we write down the size of the minimum barrier as proportional to 1 over the volume sampled, or 1 over 4/3 pi r cubed, and we then take this and divide by kT and put it into an Arrhenius expression, knowing the Marcus theory we would do things a little differently from Mott, but let's take this way, multiply by this exponentially decaying probability of tunneling with r. So here is the expression that we need to maximize. It's left as a problem for you to do in the back of the book, to take the derivative with respect to r, set it equal to 0, and find that the optimum range for hopping is this 4th root power of temperature. If one substitutes this back into this expression here for the conductance, you see in the first term that you have a minus 2 kappa r, so this is like minus 1 over t to the 1/4, which is therefore like minus t to the minus 0.25. In the second term, you have a 1 over t to the 3/4 times t. This then gives you again a term in minus t to the minus 0.25. This means that the conductance increases as temperature increases. Why? Because this factor t to the minus 0.25 decreases, it appears as a negative in the exponent, so the conductance increases as the probability of finding a small barrier becomes greater. So carriers can be mobile inside molecular solids if adequate thermal excitation is available. What is the actual transport mechanism in a molecular solid? Well, most likely in a polarizable molecular solid, charge will accumulate at an interface with a polarized metal, with the result that the electric field owing to the polarized metal is screened over a distance like the Debye length. However, it's in this region of high field that carriers can be injected owing to the field into the molecular material and then accumulate in the solid. However, if the electric potential is now constant in the solid, i.e. the electric field is zero, there is no electric driving force for current in the solid. Nonetheless, current still occurs because of the concentration gradient built up as carriers accumulate near the electrode. The equation that captures these factors is the so-called Nernst-Planck equation, shown here for current density. This term you will recognize as the field-driven current, i.e. the potential gradient or electric field, times the mobility of the carriers times their number density. This term is not important in the bulk of the material. In the bulk of the material, diffusion-driven current dominates, and so here is the diffusion constant as obtained from the Einstein-Smoluchevsky relationship, where this is the mobility of the carriers, and here is the carrier concentration gradient. So we understand then currents in molecular solids as thermally activated hopping within the bulk, a current driven by the chemical potential gradient. Turning now to another type of molecular solid, often called a molecular wire, what happens when we have a so-called conducting polymer? Well, this illustration at the top here is to show you that the mechanism of electronic conduction changes drastically if you go from a two-dimensional material, where an electron can presumably always find an unoccupied site randomly, to a one-dimensional material, where if an electron is to move from this site to this site, then an electron occupying this site must necessarily move from this site to the next. In the language of physics, this is called a transition from a Fermi liquid, as we discussed in Chapter 7, to here what is called a Luttinger liquid, if indeed there is mobility in the material. However, chemists will recognize this as simply the motion of chemical bonds along a polymer, and let me illustrate this here for the case of polypyrrole, illustrated here. Polypyrrole becomes a conductor when an oxidizing agent is mixed into the bulk, as shown here. In that case, the chain can lose an electron to the oxidizing agent. The result of this loss of an electron in removing a bond from this ring is to generate a new chemical structure in which a radical is formed at this point in order to stabilize the removal of an electron from the ring over here. This structure, however, is mobile in the sense that because this chain repeats infinitely, the delta G for moving from one site to the next is zero, and so providing there is enough thermal energy to pay the reorganization price of moving from one site to the next, this can be a hopping conductor of positive charge. Because this structure contains a radical, it's actually stabilized by a second reduction, so shown here, where now one has a carrier of charge plus 2e, which once again is free to move, providing there is enough thermal energy to pay the reorganization energy price of conductance. You can see that this motion is very far from the idea of metallic conduction. It is true that metallic conduction has been observed, for example, in polyaniline, but only in extremely metallic material made by a very specialized synthesis. This required real 3D crystallinity in the polymer. The crystallinity has two effects. First of all, it minimizes the polarizability of the material, thereby minimizing the barrier, the reorganization energy barrier to transport. And secondly, it makes the material truly three-dimensional, so the transport then can be that of a carrier in a Fermi liquid and not a Luttinger liquid.